Now that you have learned what is an optical fiber, what is an optical fiber communication, now you need to know what is that principles that govern the light through this optical fiber. Okay, so basically the two principles that guide a light through an optical fiber is refraction and total internal reflection. Okay, now you need to know what is refraction and what process is called total internal reflection. As you can see in the figure, you have an incident ray, you have a refracted ray, you have an angle of incidence theta I, you have an angle of refraction theta R, you have two mediums, denser medium and a rarer medium. What differentiates a denser medium and a rarer medium? That differentiating factor is called refractive index. As you've all learned in your previous classes, you might be familiar with the term refractive index. Refractive index is a dimensionless quantity which governs a ray of light through a medium. Okay. If you have a higher refractive index, that means you have a denser medium. If you have a lower refractive index, that means you have a rarer medium. So you can see the incident light, incident ray. Incident ray is nothing but a incoming ray. When this incident ray is incident on a denser medium with an angle theta I, the theta is called the incident angle, the ray gets refracted. Why the ray gets refracted? Because the incident ray is going from a denser to a rarer medium at an angle theta I. Okay, so this angle theta I is called the angle of incidence, and the angle theta R is called the refracted ray. The angles are defined with respect to normal. You can see the dashed lines. The dashed lines is called the normal. The angle between the incident ray and the normal is called the angle of incidence, and the angle with the normal and the refracted ray is called the angle of refraction. Okay, so the basic two principles that govern uh, the propagation of light through an optical fiber is, first of all, is refraction. The other one is total internal reflection. Total internal reflection we'll describe in the next slides. So you can understand what is a refracted ray. A refracted ray is nothing but a ray when a ray of light is incident at a denser medium uh, at the boundary between the denser and the rarer medium. Due to the difference in refractive index, this incident ray of light get bended that bending phenomenon is called refraction. So the ray that is coming out from the denser medium is a refracted ray which has an angle theta r, which is called the angle of refraction. The other one is the angle of incidence, and the angle of incidence is nothing but the angle with which the angle is incident with the normal. So next, the refractive index. As already mentioned, refractive index is a dimensionless quantity which governs the propagation of a light through a particular medium. So different mediums have different refractive index. So the definition, as you can see from the slide, refractive index is a measure of bending of ray of light when passing from one medium to another. The refractive index is denoted by the letter n. Numerically, it can be expressed as the ratio of sine of angle of incidence to the sine of angle of refraction. N is equal to sine of theta I by theta r. So refractive index can also be measured as the ratio of velocity of light in empty space or free space divided by the velocity of light in that particular substance. So n is equal to c by v. C is the velocity of light in empty space or free space. Its value is 3 into 10 raised to 8 meter per second. So next is Snell's law. Snell's law is another law in optics. The Snell's law states that the refractive index of a particular medium into the sine of angle of incidence is equal to the refractive index of the other medium n2 into sine of angle of refraction. That is, n1 sine theta 1 is equal to n2 sine theta 2. Further reducing that statement, we can write down as sine theta 1 by sine theta 2 is equal to n2 by n1, where theta 1 is the angle of incidence, theta 2 is the angle of refraction, n2 is n2 and n1 are the refractive index of the respective medium. Substituting the value of n1 is equal to c by v1 and n2 is equal to c by v2, we can rewrite the expression for sine theta 1 by sine theta 2 as v1 by v2. Again, the Snell's law can also be expressed as Snell's law states that the ratio of sine of angle of incidence and the sine of angle of refraction is equal to the ratio of velocities of the two mediums, that is v1 and v2, or it is equivalent to the reciprocal of the ratio of the indices of refraction, that is n2 by n1. So this is Snell's law. So now that we have learned what is optical fiber, what is an optical fiber communication, what is the structure of an optical fiber, that is it has a core, cladding and a buffer jacket. Then we learned what is an incident ray, what is a refracted ray, what is angle of incidence, what is angle of refraction. Then we learned what is refractive index, we learned the formula for refractive index. Then we learned Snell's law, then we have the expression for Snell's law. Now we learn critical angle and total internal reflection. So this critical angle and total internal reflection is the two main criteria which explains the propagation of light in an optical fiber. Okay, so before going in detail about total internal reflection, first we need to know what is a critical angle. So you know that there is an incident ray and a refracted ray. Okay, so critical angle can be explained as that angle of incidence for which the refracted angle is 90 degree. So when the angle of incidence is equal to the critical angle, the refracted ray passes through the boundary of separation between the two mediums. Okay, so angle of incidence for which the refracted ray passes through the surface of separation between the two mediums, and when the refracted angle is 90 degree, that angle of incidence is called the critical angle. Okay. So the next topic is total internal reflection. So total internal reflection is a phenomenon through which a light gets propagated through an optical fiber. So when a light is incident at the boundary separating two mediums, a denser medium and a rarer medium, and if this angle of incidence of this incident ray is greater than the critical angle, then this ray will be reflected back to the same medium. Okay, it will be reflected back to the same medium in which it was incident. So this property is called total internal reflection. So again explaining, a total internal reflection is a phenomenon which occurs when a propagated wave strikes a medium boundary at an angle greater than the critical angle. So when such a phenomenon occurs, the ray that is incident will be reflected back to the same medium. This process is called total internal reflection. Okay, now consider the case of an optic fiber. An optic fiber has core, cladding and a buffer jacket. As I've already mentioned, the core has a higher refractive index than that of a cladding. So when an incident ray is incident on the core at an angle greater than the critical angle, then the ray will be reflected back to core itself. Rather than going out of the cladding, this ray will be reflected back to the core. So like that the ray gets propagated through multiple total internal reflection inside the core cladding interface. This is how a light incident at a transmitter propagates through an optical fiber and reaches the receiver end. Okay, so from the figure it is clear that there are two conditions for total internal reflection to take place. One is the incident ray should go from the denser medium to a rarer medium, and also this incident ray should be incident at an angle greater than the critical angle. So you can see from the figure, first figure shows when incident angle is equal to the critical angle, then the refracted ray passes through the boundary of separation between the two mediums. The second case is a total internal reflection case where the incident angle is greater than the critical angle, then the ray will be reflected back to the same medium in which it was incident. The last figure at the bottom shows how a light is propagated through an optic fiber. This is an optic fiber. You have a dense core and a cladding. So here the denser medium is served by the dense core and the rarer medium is given by the rarer cladding medium. So when a light is incident on a denser medium, that is on the core, at an angle greater than the critical angle, the light will be reflected back to the same medium. That is, it will be reflected back to core itself rather than going to cladding. So again, the second ray, again it is incident on a core cladding interface, which when it is incident at an angle greater than the critical angle, then it will be reflected back to the same core itself. So through multiple total internal reflection process, the wave propagates from the sender to receiver.